Ratnesh?
Yes, sir.
Good morning.
Good
Shall
morning.
we start now?
Yes, sir. I can start.
Okay. Okay.
Okay, so I start.
Yes, yes, Professor, please. Yeah.
Okay, so for those of you who only managed to connect today, this is the course overview. Over the last 2 days, we had some interesting discussion about AI, large language models, and also what could be coming next. We even talk about finance and politics and trends. And in fact, some of the questions that I've been asked yesterday actually it's something that we're also going to talk about today in lecture 3. So some of the slides and contents of lecture 3 actually we already discussed some of them yesterday. So and the past 2 days instead, the first day we talk about how to represent and classify or cluster data with some basic machine learning techniques. Once again, it doesn't mean that because deep learning is the state of the art, you have to use deep learning all the times. If you have a smaller data set, or you can get good enough accuracy with an SVM, for example, it's totally fine to use SVM instead of a deep neural network. Yesterday we talked about AI, limitations of AI, and also a short introduction to neural networks. And most importantly, how we went from feed-forward neural networks to deep neural networks. So again, this was the first lecture in which we looked at data representation and classification. Yesterday, we talked about different topics in AI, including some conjecture like the plagiarism conjecture of like if we have all these LLMs generating text, then how long will it take for these LLMs to generate all possible texts? And then this slide was also quite important yesterday. It's important to clarify that although these three terms are used interchangeably, they are not actually synonyms, but a subset of each other. Deep learning is a subset of machine learning, which is a subset of artificial intelligence. So the part of artificial intelligence that we talk about until now is called subsymbolic AI. So that can be like a synonym of machine learning. And in lecture 5, we'll also talk about the other side, the other half, symbolic AI. I'm talking about knowledge graphs, semantic networks, and different kinds of knowledge representations. So yesterday we also talked about intelligence. What is intelligence? How can we build intelligence? What are the key limitations of AI? To then discuss about how neural networks work. We had very simple examples on how to build a simple neural network. One important point was also the fact that in order to be able to play and reason around some concepts, we had to kind of translate them into vectors. We had to come up with the vectorial representation. Why? Because neural networks are mathematical models. So this is important to remember for today's lecture, because here we had no choice, but because we have three types of food, we created the three-dimensional vector. So pizza was 100, burger was 010, sushi was 001, and this is how then we worked with these constants within the neural network. And the output of the neural network was, again, one of those vectors that we then translate to the specific concept. So this is also an important concept from lecture 1. We have to kind of shift to a different domain and then go back to the original domain. And this is no different from also how large language model works. They work on embeddings, and then the result is again an embedding that it gets translated into text. So yesterday we also talked about different.
बिल्कुल सही कह रहा बिल्कुल सही
Someone has their mic on.
Yeah,
Shiva.
Bhaktis, can you mute others? Maybe. Yeah, please go ahead, Derek.
So, okay, we talk about different kinds of word embeddings, and the ones that everybody is using right now is BERT, and there's many different kinds of BERT in our domain. The one that works best is Roberta. In fact, in the latest version of CenticNet 8, we actually compare CenticNet 8 with Roberta. And then we also briefly talk about recurrent neural networks, why they became popular, and also why they became outdated. And the last but not least, we talk about sequence-to-sequence model, which are also a bit outdated because now most of the tools that we are using are decoder only, but still very interesting from a point of view of meaning, encoding, and decoding. So as we said yesterday in the example of machine translation, these hidden states that are passed from the encoder to the decoder is a sort of Rosetta Stone that encodes, encapsulate the meaning. So yesterday we talked about how very high level how the sequence-to-sequence models work and how we went from modeling sequences of anything, so of types of food, like in the example of recurrent neural network, to images, to videos, and to texts. That's how we got large language models. And the precursor of large language model, if you remember, it was prompting when we were doing masking to guess what is fill in the blank word in a sentence like this. So from there, then we went into sequence generation, and that's how the generative AI revolution started. Today we have a lot of these models, and we also discussed about DeepSeek yesterday. What's the difference between DeepSeek and ChatGPT, and which one is focusing on which goal? But again, if you have other questions on this, I'm happy to continue talking about it. And last thing we saw was a very brief introduction to transformers. We had some discussions on this, but yeah, here I only put the three key novelties of transformers and some links for those of you who are interested in knowing more about the technicalities and how to build a transformer from scratch. You can look at these video lectures, and then of course you can find a lot of code on Spacey and Hugging Face. So today lecture is really about what to do next, so mostly about the future of AI, but we want to start from also some history of AI. We briefly touch on that, but I still want to discuss about some past failures of AI, because nobody tells us that actually there's gonna be another AI winter coming up soon. Actually, many people in finance already talking about some sort of AI bubble. And this is separate from the technicality. So from the technical point of view, AI is probably just going to improve and become better and better. But then from a financial point of view, it's not maybe immediate to see some returns because some of these architectures are very costly. And so that's why some are talking about an AI bubble. But before we talk about the future of AI, I want to talk about machine learning in general as a big umbrella that also includes deep learning and many different kinds of learning. So in this picture, you can also see some of those things that we discussed yesterday, like the difference between supervised and unsupervised learning, which again, as discussed, these days is not as clear cut as in the past, because then the question is a pre-trained language model supervised or unsupervised? And you could say it's both. And then but here the question is, what are we learning in fact? So this actually dates back to the question of what is intelligence, because the way we learn things sometimes is only unilateral. So, for example, the way we teach a machine learning model how to reason about something is usually only focusing on one aspect. So, to give you an example that maybe you can relate better to, is like if I showed you 1001 videos of snowboarding, then it would be wrong for me to expect that you would be able to know how to snowboard if you've never done that before. I don't know why you guys are so noisy today. uh, so this question is about what is it that we're really learning? So it goes back to the question of what kind of intelligence are we really trying to emulate? And in many cases, we are only focusing on one type of task or one type of intelligence. So this maybe relates to the image of the slide of multiple intelligences, where one thing is to know the theory and another thing is to know the practice. One thing is IQ, another thing is physical intelligence. And this is important and also relates to back to the problem of one of the limitations of AI, which is that it depends on the training data. Here is an old example of one of the first driverless cars that took down one of these robots. And why was that? Because in the training data set of the driverless car, there were no robots of this type. It was mostly trained on pedestrian with two legs moving. And this robot didn't have any legs, and so the car simply didn't recognize it. So this again, it's important. It's an important question. What is it that we are learning exactly, and how is the learning happening? And the first principle is that we must not fool ourselves. So it's important to understand the limitations of AI so that we know what are the things that AI can do and the things that the AI can't do. And this is a problem that led us to have those so-called AI winters in the past. And these were mostly happening because there were like a lot of expectations from a general public that then were met. So all these dips or AI winters here happen when basically people thought that AI wasn't working. There were no more research fundings in AI, no more business investment in AI. So this is something that has happened before, and it may happen again in the future. And it could be for a technical reason or for a financial reason. But AI fails are actually a lot in the history of AI. One is something that we mentioned yesterday. Was Amazon that was using AI as a recruiting tool, and then later on realized that the AI was using gender as an important feature to shortlist candidates. But then there are many other examples. Lucky these days you don't hear about that anymore, but in the past there were many accidents caused by driverless cars. And this is also an important question of accountability. So in this case is who is really responsible when accident happens. And last but not least, there was also this hotel, not sure if you heard it, in Japan, that decided to just be run completely by robots, but after a while, clients got tired of it because the robots weren't working that well, and they just wanted to go back to talking to a real human. There's also this Thai tweets chatbot by Microsoft. I don't know if any of you remembers that. And they just created this chatbot and they put it out there to supposedly learn from the interaction with other users. Initially, everything was very sweet and nice. Things started to go sideways when Thai, which is again a Microsoft chatbot, started to say that the PlayStation by Sony was better than the Xbox. And then things they just went down spiral, like they had to literally kill the chatbot and stop the project because the chatbot was becoming increasingly biased and racist. So the problem here is, as we discussed with one of you yesterday, statistics are good when you're working with numbers, but not so much when we're working with text. That's why it's important for us computer scientists to still collaborate and work with linguists. And so the problem here is, again, that we have to translate text into some sort of numbers, some word embeddings, and then work with those embeddings. But sometimes um, communication language is so much more than that. There could be some hidden meanings, there could be metaphors, there could be sarcasm, there could be some common sense required that it's not in those numbers. And in fact, in general, statistics are a good tool that we use for data analytics and for many things in our civilization, but it's not that you can do everything with stats. For example, if I ask you whether which one of these two here in this image is more scary, many of you would probably say the one on the right, the shark. But the truth is that statistically, coconuts kill more people than sharks every year. But of course, emotionally, we don't feel as scared of the coconut as of the shark. But this is just a simple and funny example to show you why statistics are good in some cases, but not always. Another big issue that we already discussed about some of current AI algorithms that are black box is transparency. So when you have to, if you just care about accuracy and you're working on a toy problem or an application that doesn't involve ethics or human lives, then you don't care. But if you're using AI in the context like healthcare or other situations where you need to know what the AI is doing, then the big question is, do I rather use an AI that is less accurate but with some sort of some degree of transparency or a very accurate AI that does? And this happened a few times already. In this old example, there was this AI that was able to tell better than human doctors which patients was going to die soon, but nobody knows why. There was no way to open this black box to see exactly what was the reason for that. There are other funny examples like Nigel. So today we could say that AI is a bit like this guy, Nigel. This is a Kiwi, a guy from New Zealand who doesn't speak French, but some years ago, I forgot when this was taken, but a few years ago, he won the French Scrabble Championship without knowing French. And so you don't really need to be able to understand or speak the language. As long as you are good at sequencing letters and make up words, then it's good enough for you to be considered intelligent or to win a prize. And this is very much what large language models are doing. So we don't have to get confused when we say that at this point we can achieve high accuracy or human-like accuracy on many NLP tasks. That's not equivalent to say that we have created machines that are as intelligent or even more intelligent than humans. As we discussed yesterday, we are talking about two different kinds of intelligences. Number one is biological and one is artificial. And number two is also about the difference between expert systems and intelligent systems. Most of these models, AI models, are very good at doing just that one thing, and they can't pretty much do anything else. So one thing that we'll discuss also later is the problem of symbol grounding. So even when I use word embeddings or simply when I use those vectors that we have fabricated before, the problem here is that it's not true. Like in our brain, it's not like that pizza is is represented simply as a vector. You could say that is maybe stored in our brain in the form of some electric signal, but still it's so much more than just a vector. It's connected to so many memories and so many facets of the meaning of food like pizza, which entails like how you eat pizza, how it smells, how it tastes, how it looks like, and so on. And this is a problem that is still a problem today. We haven't solved the symbol grounding problem, even for the fastest and smartest large language model existing. They don't really have this meaning grounded. Yes, they can talk about all the different kinds of pizzas, how to make pizza, but they don't really have a representation for pizza. When you ask questions about pizza, they just blurb out an explanation that is maybe generated from documents that answer this question. So in order for us to have an AI that we can really trust, we also need to look at these aspects. We have to have AIs that are not just playing with numbers and associating concepts with embeddings, but also some sort of representations. That's why, as I mentioned yesterday, we are in my group, we are trying to work on neurosymbolic AI, an AI that is hybrid, an AI that is using large language models together with knowledge representation. But don't worry, we'll talk about this again in lecture 5. Now I want to talk again a bit about large language models. This is the slide that we were already discussing yesterday after one of you asked what's next after large language models. There are many different definitions of large language model. I like this one from Investopedia because it's simple and non-technical, and it focuses on what are the strengths and weaknesses of large language models. So first of all, the definitions say that it's a tool to summarize, translate, predict, and generate. So once again, as I said many times, a large language model is trained, optimized for plausibility. The goal of a large language model is not to give you the absolute truth. It's just to give you an answer that sounds reasonable, that sounds plausible. That's why many people actually got in trouble because they were like there were some legal cases where a lawyer was asking ChatGPT to provide some examples from the past. ChatGPT did so, but then it turned out that these cases never existed. They were just generated. So they sounded very real, they sounded very plausible, but actually they were simply not real. So that's one of the biggest limitations of large language models today. They don't do any fact checking, and that's why people are looking at other systems like BRAG system, retrieval augmented generation, or other system that can ground the production, the outputs of large language model into something tangible. And then the second part in this definition is that they generate what? They summarize, translate, predict, and generate what? Human sounding text. So once again, plausibility is the goal here. There is no cognitive architecture there. There is no symbol grounding. It's mostly based on data. When there is not enough data available, it hallucinates. So we can talk about hallucination maybe later. It's not necessarily a bad thing. For example, when you talk about computational creativity, hallucination is good because given some missing data, it can generate something completely new based on the little data available. But in cases like question answering, information retrieval, then hallucination is bad because then it's like the system is trying to make up some data that it doesn't have. And last but not least, this was the key point of our discussion yesterday. Their goal is to convey ideas and concepts, or in other words, to give you an answer. And they don't do stuff for you. They don't, first of all, they are not personalized. It's not like they know your personal preferences much. And now some are working on this as well. So now ChatGPT does have some degree of personalization, but still we are far from having a personalized chatbot. And finally, they don't do things for you. And people are already working on this. They call it agentic AI or agentic RAG. But for now, most of the things you see on the market, like ChatGPT and DeepSeek, they just give you an answer and they don't do stuff for you. So this is also related to the example that we gave yesterday when I was talking about like a chatbot. Now every bank has a chatbot. Most of the times you have to talk to a chatbot, but if you ask the chatbot to do something and then a chatbot tells you, okay, then you never know whether the chatbot really understood you and really did that thing for you, or it's just giving you once again a plausible answer. So this goes back to the concept of the Chinese room argument. It was called Chinese room argument because back in the days, Chinese was still like considered very difficult language, not as spread out as it is today, and here the conjecture was that if you are a Chinese speaking person, write something and insert it into this box, into this room, and then inside you have someone who doesn't speak Chinese, but he has a sort of rule book in English that tells the person what to blurb out as a reply given the question. So again, like a question answering system. Then even considering, assuming that the output is perfectly correct, then the big question is this room, is this system intelligent or not? From the point of view of the user, it is, because you ask a question in Chinese and you get a perfect answer in Chinese. But the truth is that inside, there's not really someone that can speak Chinese. So some say that it's still an intelligent system because then the rule book represents the intelligence, and how the rule book is used represent intelligence. But then again, it's just maybe it's just playing around some rules, and it's not maybe it's not if we talk about like from a cognitive point of view, I wouldn't define this as true intelligence. And some AI researchers brought this back up. This Chinese room argument actually dates back to the 70s, but someone just brought it back recently in the context of LLMs. So LLMs are extremely good at answering questions, but how can we be sure that they know what they're doing, that they are truly understanding our words? And in this person, Blaise Aguirre Carcas, even went to the extent of comparing LLMs to a person with disabilities and superpowers, in a sense that LLMs, ChatGPT, for example, doesn't have eyes, doesn't have sense of taste. So in that sense, it's disabled because can only see the world through words. But then, yeah, this had a lot of backlash from disabled community, but I don't want to get into that. What's interesting here, the big question here is, we use an LLM, it gives us good result. Do we care whether it's truly intelligent or not? And if we care, how can we answer that question? So language, we don't have to forget that the way this large language model works is again on language. So let's not forget, one key point here that we also made here is that they are just language model. They just model language. It's not like they do anything else. They don't take actions for you. And so here also there are some very interesting linguistic theories that we should look at. And some say that actually language affects the way we think about anything, including, for example, for some languages that use feminine and masculine in different objects in different languages can be either feminine or masculine, and depending on that, we have a perception about these concepts that changes based on whether we use them as masculine or feminine. So masculine objects usually are associated with concepts like strength, while feminine about beauty. And we also realized that LLMs have this kind of bias in some of our recent works. We did a lot of this kind of bias comparison with LLM that you can look at if you are interested. And there are different theories, linguistic theories that say the opposite, that it's thought that affects language. And so different peoples in different parts of the world, they came up with their own language because of the way they thought, because of the things that they did. But so it's important not to forget that language is just it's just a standard, same way as we have different standards in even just in the West to measure things, to measure how long something is, how heavy or how hot or cold something is. Why? Because there is not one unique, general or universal way to do that. And unfortunately, we don't have many of those universal things. And you could say that maybe mathematics are universal or musical notes. And there are very few things that are universal. And language is the same as all these different metrics, all these different standards. We had to come up with some sort of way to communicate with each other in a written form. And different people, because they were disconnected from each other when there was no internet, they had to come up with different standards. So it's called natural language processing because one thing is natural language and one thing is artificial language. So artificial languages are languages that are made up and including like even programming languages, but better examples could be like Esperanto or even anybody can come up with their own language. There's a study that says that twins usually they make up their own language in the first few years of their life, then they tend to forget it later on. But as long as you come up with a shared representation to communicate with someone, then that can be considered a language. But one thing that we don't have to forget is that, for example, a large language model is only working with text. Could be characters, could be letters and sequences of letters and words. But actually, the way that text was actually born was through the sound that some words make. Many of not all of them, like Chinese characters, don't do that. But for example, text and alphabet are there to represent a sound. The combination of different letters of the alphabet are there written so that they can actually replicate a certain sound that we make when we speak. And this is important because then we are actually 2 degrees away working on meaning when it comes to building a large language model. And this is, you can see it also with different languages and how they are, the encoding and decoding of different languages. So, and you can see in some examples, even in English, where a word actually sounds different from how it's written, or in Chinese, where every character is there for representing a specific sound. That's true, but then it's done very differently from how the alphabet is combined. And this is also important for those of us, like our group, working on social media analytics, because then when you look at microtext, which is something I will discuss in next lecture, it's also important to be looking at phonetics because, for example, in social media, there's a lot of usage of the number 5 for different purposes because in Chinese, the number 5 is wu, and it replicates, emulates somehow the sound of someone crying when you have a lot of 5 next to each other. But in Thai, actually, number 5 is ha, so many ha, one after the other, replicates the opposite emotion of laughing or having fun. And some anthropologists actually say that the fact that we humans, unlike our other species, and even like our even as compared to monkeys, and one of the possible reasons why we became so much more different and intelligent as compared to them is probably thanks to this FOXP2 gene that allowed us to make different sounds. So in a way, this is actually a very interesting theory that intelligence was in a sense enabled by the fact that we could create many more sounds than other animals. So it's a bit like if you think of any animal, there's not many sounds that they can make. And so maybe that was a limitation for them to not evolve into something more intelligent. The fact that they didn't have the possibility to utter more than maybe just a couple of sounds. So this is another thing to take into account. And here I put a funny video that maybe you can watch during the break, which is about how to replicate sound. This is also related. For example, if any of you reads comics and you have to replicate or emulate a sound in a comic book, then you have to come up with some sort of code like BAM or some onomatopoeic words that represent that sound. But all of these to state once again that working with text is actually, first of all, text is just a standard, and second, it's just a representation of the sound that we make when we communicate with each other. And then this sound is also then connected in our brain to some sort of knowledge representation. So intrinsically, this is very different from how a large language model works. And in fact, the next slide is exactly about this. Many say that large language models are learn the specific language the same way as we learn a new language. But that's not very much of a fair comparison because, for example, if I'm learning two languages that are very similar in terms of sounds, and there are many of these. So if you take like European languages, like Italian, Spanish, French, they are all very similar, then it wouldn't be fair to make this comparison, right? So to make the comparison more fair, we could say, okay, maybe it's like us trying to learn a language which doesn't have common phonemes, as a language that sounds completely different from the one that we know. So now the question is, like, for example, if you take one of the three languages that I mentioned before, compared to German, which is sounding very different, and also the phonemes of the makeup words are completely different from the lemmas and root words of Italian, French, and Spanish, then now the question is, would this be a fair comparison? And the answer is still no, because then you also have different ways of representing text. For example, Russian uses Cyrillic, Chinese uses different characters. You can have Sanskrit, you can have Japanese characters or Thai. So okay, let's take a language that doesn't have a common alphabet then. Would it be fair they still have a common structure? So many languages, although they have no common phonemes and no common alphabet, they still have the same structure like subject, verb, and object. And we'll talk about this in the next lecture when we talk about text chunking and NLP tasks. But then, so we are still not. So we can take, for example, maybe there are some tribal languages that are completely different from the languages that we are used to that don't have this kind of structure. So then would it be a fair comparison of a large language model learning language the same way as we do if you don't have common phonemes, common alphabet, and common structure? Still not a fair comparison, because even if we are learning this weird tribal language that doesn't have a common structure, alphabet, or phonemes, we can still use our common sense as a grounding for anything that I learn from this language. So the only fair comparison would be us trying to learn an alien language, where you have a language that is completely different from ours, so with different structure and no shared common sense. So that's how difficult it would be for a large language model to truly understand meaning and truly learn language the way we do. Then there's much more to talk about, because in fact, as we said, there's really no cognitive architecture behind large language models, but these at least to reason on what it means really for a large language model to learn and master a language. But nonetheless, many people like to say that, they like to make that comparison of large language model learning language as we do, the same as they do for deep learning in general. But that's very far from the truth. This is a nice metaphor, a nice analogy, but it's not true. We do not learn languages like a deep neural network. It's completely different. And a deep neural network learns language in a very bottom-up fashion using training data. And we do learn some of the language like that, by example, but not all. There's a lot of stuff that we learn in a top-down manner by using common sense. We'll talk about this in lecture 5, but this is just to say that computer science is full of this kind of analogies and metaphors that are actually, they're nice analogies, but they are not true. Sometimes they are confusing. The same goes with neural networks that we just saw yesterday. It's cool and nice to say that the deep neural networks mimics the structure of the brain, because it kind of looks like the synapses in our brain, but our brain doesn't work like that. Remember yesterday when we took the nodes, the edges, calculated the weights, and used hyperplanes to separate the perception space? That's not how a neuron works. That's not what's happening in our synapses. So it's also important not to get confused here by these analogies. I'll go on and talk about some of the miracles of the brains before I go into talking about the pillars of AI, but I just want to stop a bit to see whether there's any question.
You can unmute it. Hello, Ratnesh. You can unmute others if they have any questions.
So what do you think, Asif? Shall we take a break now or later?
Yeah. Eric, you can take a break. Yeah.
So maybe you guys have time to think about what we talk about and see if you have any question, and also watch this funny video. I hope the link still works. If you guys find any link in the slides that doesn't work, please let me know, especially all those links that I give you at the bottom of each slide. I should have checked it if they still work. But if you do find any link that is broken, please let me know, and I'll try to fix it, like to find the original video or resources. Okay, so shall we take a break now?
Yeah. Eric, we can take a break and then maybe we can start. So by that time, maybe if the participant have any questions, they can think and then maybe they can ask you.
Okay, okay.
Okay.